Sketch a graph of the function f of x equals -5 times quantity x plus 9 to the fourth power times quantity x plus 3 to the sixth power times quantity x plus 2 to the third power. Then identify the end behavior, the zeros of the function with their multiplicities, and the behavior at each zero. All right, let's start with something more familiar, like a linear function. I have it written here, f of x equals 2x minus 3. Now, to put it in a form that we're more accustomed to working with, I'm going to replace the f of x notation, the function notation, with the y variable. And I'm going to simplify the 2 times quantity x minus 3. I'm going to distribute the 2. So I have 2 times x is 2x, and then 2 times -3 is -6. Now, the function is written as a linear equation, which is a degree 1 polynomial. And it is in the form of slope-intercept form. So recall, slope-intercept form is named slope-intercept because when a function or a linear equation is written in the form y equals mx plus b, we are easily able to identify m, the coefficient of x, which is our slope, which we sometimes refer to as the rise over run from one point on a line to another, or the steepness of the line. And the b represents the constant term, which is just a regular number with no variable attached to it, and that is known as our y-intercept, or the place where the line will cross the y-axis. And since it is a place on the y-axis, anywhere along the vertical axis, any point on the y-axis will always have a 0 coordinate, or a 0 for the x-coordinate, right? All right, so we know that any y-intercept is going to be of the form 0, comma b in general. All right, knowing that, or just having reviewed that, we can sketch this function by using the y-intercept -6. So that will be the point 0, comma -6, or the point lying on -6. I almost went to +6. I need to go to -6 on the y-axis. Okay, there is our starting point. Then we can use the slope given here, 2, which we can write as a fraction as 2 over 1. So that means for every time we go up 2, we're going to go to the right 1. So up 2, that's moving 2 places in the positive direction on the vertical axis, and then moving to the right 1 positive unit to the right is 1 positive in the horizontal direction. Then up 2 again and over 1. If I continue to do this, it will form dots that I can connect to create my line. And I kind of messed that last one up. Let me do this. So if I keep on doing this, up 2 and over 1, you'll see my line forming. I could also, since it's positive, I could also do down 2 and backwards 1, because a negative divided by a negative is a positive. So I could also, from that first point, have gone down and backwards 1, down 2 and backwards 1. And that's going to create a nice linear pattern that I can connect. And really, we only needed 2 of those to create a line, because as soon as you have 2, you can connect those with a straight edge. And I'm trying to make this as straight as I can on my slippery monitor that I'm drawing on here. But that's a very rough sketch of what the line should look like. Okay, now there's a couple of things I want you to notice here that we're going to be transferring over to our more complex problem. And one of the things is the end behavior. So notice that the ends are opposite. So we have the left end going down and the right end going up. Now, that's because, or we could have known that ahead of time if we had taken note of the fact that x has a power of 1, and that's the highest power on x. which makes this a degree 1 polynomial. And since that is odd, we should expect the ends to be opposite. If it had been an even degree, we would expect the ends to be pointed either both up or both down. But because it's odd, they're opposite. Also, notice that the left end is down while the right end is up. So from left to right, we read graphs from left to right just like we read words and sentences from left to right in the English language. This graph read left to right, the line is increasing upwards. And notice that our slope is positive. So with a positive slope combined with an odd degree, we would know ahead of time that the left end should be down and the right end should be up. Doing a similar example, but having a negative lead coefficient will produce a very similar type of line, but the ends will be reversed. Now, to see this, let's just go ahead and simplify it. So we'll distribute the -2, -2x, and -2 times -3 is +6. So this time now we're going to have our y-intercept on +6, and then using the negative slope of 2 over 1, -2 means I'm going to go down 2 and forward 1, down 2 and forward 1, and that will create my line like that. Or just like I can see the slope of 2 as -2 over +1, I could likewise see it as +2 over -1, meaning that from that same starting point, I could go up 2 and backwards 1, up 2 and backwards 1. Okay, so that's just a review of how we graphed lines. Again, a very rough sketch. It should be a lot straighter, but you get the point that now we still have opposite ends because we still have an odd degree polynomial, but now notice that from left to right, there's a decreasing behavior here where the left end is pointed up and the right end is pointed down, right? Let's jump over to our complicated example, which is this polynomial here. Now, let's see if we can figure out how to extend what we just learned using all of this. Now, I don't want to have to work this out, but I want to be able to use that lead coefficient right here, along with the powers to somehow figure out whether my ends should be pointing the same direction or opposite directions, and if they're opposite, should they be left to right upwards or left to right downwards? Or if they're the same, pointing the same direction, should they both be up or should they both be down? So I am going to first figure out what is the highest power on x when I simplify this? Well, that's going to be quite a lot of work to do. So if I simplify this like I did the line, I'm going to have to do a lot of work. I'm going to have to start simplifying. Look, I'll leave the -5 out, and then I'm going to have to write this quantity x plus 9 to the power of 4. I would have to expand that to x plus 9 quantity times x plus 9 quantity, 4 of those. And then the x plus 3 6 times. Oh my gosh, right? You can see how this is getting a little crazy. I'm going to have to do so much expanding, and this is just expanding it. I'm just rewriting. I'm not even doing any simplifying yet. And then the x plus 2 3 times, right? So that's a crazy looking polynomial if I've ever seen one. But just by doing that, I can quickly see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 x's. So my highest power of x is going to be 13. And if I add all these together, notice 4 plus 6 is 10, plus 3 is 13. So this does have a degree of 13. And I do have a negative lead coefficient. So being that I have an odd degree, my ends are going to be opposite ends. And since I have a negative lead coefficient, if this were just a regular line, I would expect it to be going down, like a line that has a negative slope. But since this is a degree 13, there's going to be a lot of other crazy stuff going on in between the ends, but still the ends are going to be similar to a line with a negative slope. So I know that the left side will be up and the right side will be down. So that is the first part of this problem, is to choose the end behavior. So I'm going to choose left side up and right side down, right? And we can go ahead and check that. There we go. Okay, so far so good. And I was going to also show it for like other polynomials you may have seen in the past that are a little more simple, like this one, 2 times the quantity x plus 3 squared. That one's a lot easier to simplify if we were going to spend the time doing it. We could say it was y equals 2 times, then we could expand x plus 3 squared to be written as x plus 3 quantity times itself. And then FOIL the inside, so we're going to multiply x times x to get x squared, x times 3 to get 3x, 3 times x to get another 3x, and then 3 times 3 to get 9. Then we could combine like terms so that the 3x and the 3x are combined to be 6x. And then finally we could distribute the lead coefficient, 2x squared plus 12x plus 18. Okay. And so that all that to see that this is a degree 2 polynomial, which means even, which means same end behavior. So this one's either going to have both ends pointed up, so it'll be a parabola, a U shape, both up or both down. Okay, it could be either one of those. And how do we choose? Well, again, we're going to look at that lead coefficient, which in this case is positive. So it should be both up, okay, because it's positive. If it was a negative lead coefficient, we would have said both ends down. And then something like this, if we were to expand this out, we would have 2x times, all of this is going to x plus 3 quantity squared simplifies to x squared plus 6x plus 9, like we just saw. And then x minus 2 squared would be x squared minus 4x plus 4, if I FOILed it all out. And then if we continued to multiply these two polynomials together, notice I would get x squared times x squared would give me x to the 4th. And then I could continue on, x squared times negative 4x would be negative 4x cubed. And I could continue on in this way, but what I really want to notice is that the highest power on this part of it would be 4, and then I've got one more power of x on the outside. So when I go to simplify that, I would end up with 2x to the power of 5 as my highest power on x with a lead coefficient that's positive. So again, without doing all the work to expand this out, I could see that I have a degree 5 polynomial, which means it's odd, and that means the ends are going to go opposite. And since the lead coefficient is positive, I know my ends are going to both, I know my ends are going to be similar to a line with a positive slope. So if I just picture a line with a positive slope and what those ends would look like, and then erase the center, then I have the end behavior for my degree 5 polynomial. There could be a lot of other stuff going on in between the ends, but I know at least what the ends will look like. And that is going to help me with some other information to sketch the polynomial. Okay, so that was the first part of this, is to determine how the ends should behave. Okay, so next we're going to find some more information to get more of the sketch worked out. Okay, so far I just know that my left end is down and my right end is up. Or wait, was it the other way around? Forgot what my polynomial was. Let me pause so I can clean this up without taking too much time in the recording. All right, so the next part of this, we are supposed to find out what the zeros are and then note their multiplicity for each one and the behavior of the function at each of those zeros. Now, to again relate it back to something more simple, we want to first talk about what do we mean by a zero of the function. So please note that if we were going to have the function equal 0, then we would literally change the function notation to just 0. So the question is, similarly, what value of x would make the y value equal 0 or the function value equal 0? Function notation and the variable y are interchangeable ways of referring to basically the same thing. So we are essentially trying to solve the equation for x when y is equal to 0. Okay, so what we're going to do is inverse operations until x is alone. So we'll go ahead and add 6 to both sides. So this is, we're using the line because it's a little simpler. And we want to relate back to things that we're already familiar with. Okay, so if I add 6 to both sides of the equal sign, then the negative 6 gets canceled out to a 0. And then I have the new version of this equation, 6 equals 2x. I can then undo the multiplication of x by 2. And to undo multiplication, we divide, dividing by 2 on both sides. Then I get 2 divided by 2 is 1. 1 times x is just x. So then I get essentially x equals 3. So 3 is a 0 of this function, okay, the function f of x that we started with. Notice that if I plugged 3 into the original form of the function that we started with, if I go ahead and put 3 in where the x is, then 3 minus 3 is 0, 2 minus 0 is 0, and so we get a function value of 0. And notice that you can see the function is crossing the x-axis at x equals 3. And what we know about the x-axis is that everywhere along the x-axis, any point that you grab on the x-axis is always going to have a y value of 0. And that is actually the equation of the x-axis. It is y equals 0. Similarly, the y-axis also has an equation, a vertical line, and this one would be x equals 0. Because everywhere you go along the y-axis, x is always equal to 0. Right? So we have a 0, in other words, an x-intercept, a point on the x-axis where x is equal to 3. All right? Now, if we jump over to our more complex example, when we find the zeros of the function, so we're actually doing this part, step 2 of the problem, find the zeros of the function. So I'm really just taking each quantity factor and setting it equal to 0 because I know that whatever value would make that factor equal 0, it's going to zero out the entire function because these things are all being multiplied. And so all it takes is one factor of 0 to make the entire function zero out. So if I take the insides of each set of parentheses and set those equal to 0 and solve for x, then I will have located all of the x-intercepts, or in other words, the zeros of the function. So I should have an x-intercept at x equals negative 9. I should also have one, and then you can kind of tell that you don't necessarily need to go through the trouble of writing them out and then solving like this the long way. You kind of get the idea that it's always just that number with the opposite sign. So x equals negative 3, that's going to be another 0 of the function. And x equals, what's it going to be for this one? Yep, x equals -2 for that one. So I'm going to go to -2 and have another 0 of the function. Now, we're going to pair that along with the fact that we've already decided that with an odd degree, we had opposite end behavior, and being that we have a negative lead coefficient, we had the left end pointing up and the right end down. Okay, so I know that coming from that last x-intercept on the right, we're going to be going downwards, and from that first x-intercept all the way on the left, that end would be going up, right? Now the question is, what is the behavior at each 0? Am I going to go through the point, or am I going to bounce on the point and kind of turn around? Okay, that's the question we're answering next, the behavior at each 0. Now, in order to answer what the behavior is at each 0, we have another step, which is to note the multiplicity of each 0. So previously we found each 0. We found -9, we found -3, and we found -2. Those were the 3 zeros of the function. Now let's talk about the multiplicity at each one. So the 0 at x equals -9 goes along with this factor, this quantity, x plus 9 to the power of 4. So that power of 4 is actually the multiplicity of the 0. And the 0 of -3 came from the next factor to the power of 6, so that has a multiplicity of 6. And the 0, -2 has a multiplicity of 3 because the power is 3. Okay, so now that we know what all the zeros are and what all their multiplicities are, we are almost done with this problem. Because now that we know the multiplicities, we can tell what the behavior at each 0 will be. So I'm going to come back to my sketch for a moment. Okay, so at x equals -9, the question is now, what is going to happen there? Is it going to go through? Is the function going to draw through? Should we draw it through? Or should we turn around, just touch it and turn around? Okay, so I'm going to say that we touch it and turn around because we have an even multiplicity. The multiplicity of that one is 4, and whenever we have an even multiplicity, we're going to touch and turn around instead of going through the 0. The next one has a multiplicity of 6, so we know that that one also is going to be a touch instead of going through. So here is the 0 at x equals -3. We are going to be touching it. But notice that since we're above the x-axis now, we know that somewhere we would have turned around to come back to that 0. And now we're going to be approaching it from above and again touching it and turning around. Then the last 0 has a multiplicity of 3, which is odd, which means we're going to go through that point. Now, if it was a power of 1, we would go through just kind of smoothly and straight. But if it's any odd power above 1, it's going to do a little bit of a wiggle. Now, it's hard to show this because it's so tiny, but I'm going to attempt to show you the difference. So if it had been a multiplicity of 1, what we would see is that it goes just nice and kind of smoothly, almost straight, maybe a little curvature, but mostly straight. And then if it's got a power of 3 or higher, it wiggles. So what I mean is like that, kind of like a, I don't know how to explain that, a jog, I guess. And the higher the power, the more of a jog you'll see. So like if it was a power of 5, you might see it do more like that. If it was a power of 7, you might see it flatten out even more as it goes through the point. So this though is just the power of 3, so it's just a little bit of a wiggle. It's not too much. So now I know the rough sketch of this. Now, why do we say it's just a sketch instead of just saying it's the graph? Because we don't know some things still. There's still some things that we have not figured out in our process yet. So it looks something like that, okay? What we have not figured out yet is how high to go in between when we bounce up. We just know, that somewhere up here could be high up, could be kind of low. And then same thing through here. We don't know how high it goes. Does it go shoot way up and come back down? We don't know that part of it. So this is just a rough sketch of our function. Okay, now we can do more investigating to give us more certainty on what to do in those sections that are still unknown. So like this part right here is unknown, this part right here is unknown, okay? Now we can do more investigating simply by taking values of x and plugging them into the function to find out, how high it would be. So since I have a 0 at x equals -3 and I have a 0 at x equals -9, I might try to go right in between those, maybe right in the middle of those two, which would be at, say, -6. So if I went to -6, I want to know what point should I be at? How high should I go when x is equal to -6? And to answer that question, all I would have to do is take my function that I originally started with and replace each of the x's with a -6, and then simplify until I had a y value that would tell me how high to go, right? But we weren't asked to do all of that here. So really all we need to do is grab the picture that matches the behavior at each 0. So I'm going to just put our sketch side by side with our choices. And so notice that the behavior at x equaled -9 was a U-shape facing with the ends pointing up. And at -3, we had the same kind of behavior. And at -2, we had a wiggle through coming from the top. So notice there's two options here. Instead of choosing this one over here, it makes sense to choose the one that's up on the left, coming towards the x-axis from the top, and then going below the x-axis down towards the right. So it matters, and that's why we need to sketch it out, okay? Because if all I did was say, well, I can see that the multiplicity of -9 is even, how would I know whether to pick the U shape that's facing upwards or the one that's facing downwards? I would only know that if I had done my sketch out, or if I could at least picture it. So it's really getting a good sketch of your function depends on all of these steps. The end behavior combined with where the zeros are, or the x-intercepts, combined with what the multiplicity of each x-intercept is, or each 0, and then that will help us know what to put in each section. So I hope that was helpful.